Today we're starting to talk about integer programs. So integer programs are linear programming problems, just like we saw on the first day, on Tuesday. And the only restriction is that the variables have to be integer. Now, you recall that from yesterday, I mentioned that all network programming problems can be, when they're solved, as long as the injections, if there are injections, and the upper and lower bounds are integer, then the solution will be integer. So we don't need to use integer programming. It's just a byproduct of network programming. But that is for problems that can be formulated as networks. The problem that we did on the first day with the number of chairs and tables cannot be solved as network. There are relationships such as the lathe and the drill constraint, which cannot be captured. We cannot multiply flows by 3, by 2, by whatever. If you try to draw a network for that problem, you won't be able to. So we now have a problem. How do we make sure that we get integer chairs or integer tables? Now, if we're talking about if the units in this problem are in thousands of chairs and thousands of tables, so what this is telling us to produce 2,500 chairs and 2,500 tables, that's not a problem. Even if you have some solution which had many decimals, you could round off very easily and get an integer number of chairs and tables. We would not need to specify that the chairs and tables have to be integer. But what happens if we are dealing with really large chairs or really large and expensive tables, and we really need to know how many chairs and how many tables we produce? Well, if that's the case, 2.5 and 4.5 just doesn't cut it. And so the question is, how do we do that? Well, in terms of how do we do it practically, it's very easy. If we go to data. Sorry, if we go to view, data, solve. If we go to data, go to data, we go to solver. We open up solver. We can add a constraint, and I'll show you. So what we want to do is we want to add a constraint so that these two cells, we want them to be an integer, and solver provides for that. You may have noticed it before, but not really focused on it. There's an option. Besides the standard less than or equal or greater than or equal, there is a setting integer, int, or you can make binary variables, in which case it's 0 or 1, but we'll talk about that a little bit later. Right now we want them to be integer, and then we say okay, and so now we've added that constraint, and now we go and we solve, and we found a solution, and we make 1 chair and 5 tables for a maximum profit of 11. If you recall before, we imposed this integer restriction. The maximum was 11.5. So we have an additional constraint that these have to be integer, and we have to then live with a profit of 11. And this is the solution. Unfortunately, the algorithm for solving integer programming problems is not as standard and is not as efficient, not nearly as efficient as the linear programming method. We'll talk a little bit more about methods next week. There's a method called branch and bound, which is at the core of all integer programming methods, but it really involves an extensive enumeration. In fact, there is another solution that gives you the same objective. We can try to see what it might be. Well, let's say if we make this 2 and we make this 4, well, we do worse. If we make this 5, it's not feasible. Maybe we go back to 4 and 2 and 3. Here we go. Well, 3 and 4 gives us 3 chairs and 4 tables by trial and error, gives us also a profit of 11. We have a spare hour of the lathe. We are full out on that. We use all of the drill hours, and that's it. Now, this trial and error, it really is what goes on, a little bit directed trial and error, what goes on in integer programming problems. And that's why many integer programming problems cannot be solved within a reasonable time. I teach a graduate course, and one of the first things that students have to do is pick a problem that takes more than an hour of compute time. And it's not very hard. It doesn't take huge number of variables or number of constraints to accomplish that once you insist that your variables are integer. So the solution methods are not as efficient, but the power to formulate problems becomes much enriched. And that's what we're going to talk about next.